All right, welcome to part 2 of GAME 2005 in the fall 2018 semester at George Brown, and it's part 2 of our broadcast. We did part 1 on Tuesday. Today's Friday. We're doing our lab portion. So again, I only try and record the labs on the last day of the labs. We have 3 labs, 1 on Tuesday, 1 on Wednesday, and 1 today, or tutorials, however you want to see them. I talked about last time who I am and all that kind of stuff, but one thing I did want you guys to focus on was, is this link here for the playlist, because I do have a bunch of videos from last semester that you can view ahead of time, so that way you can, kind of get ahead in terms of, watching them. I recommend you watch the next video before I produce my new one. And that way, there's a good chance you'll have some good questions, and maybe I can fill in some of the gaps that you have when I see you at lecture or lab. So that's the playlist link. I've also put this link up on Blackboard now. The other one that's really important is this one. I know that some of you have already joined me on Slack, but please join me on Slack. I'm going to do a lot of announcements and all that kind of stuff on Slack. I use Slack as my primary mode of communication more than email. I use email as well, but that will be the second line of defense, if you will. So please connect with me on Slack. This is the link, and everyone should do that. I also put up an announcement on Blackboard on Wednesday, which is all around downloading at class, because we're going to be using an attendance tracker starting next week. So for your lectures and your labs, I'll ask you guys to log in, and if you attend your lecture in your lab, there'll be a QR code that'll allow you to, to kind of access. And what that'll do is it'll track your attendance. Now, what does that do for me? What do I want you to be, in attendance? Well, as we know, there's a correlation between attendance and marks, and especially for math and physics and science and any of that kind of stuff. It's really, really important that you attend, that you're part of the lecture, and part of the labs, you ask your questions and all that stuff. Attendance is not enough, though. You have to kind of participate as well to get your bonus marks. So starting next week, I'll be doing little exercises that you can hand in for a check mark. So I'll check off that you've done, and if you've done it, then you'll get your attendance mark, right? At the end of semester, I'll kind of put all the marks together, all the little check marks, and see how many times you've attended and participated. And then I will give you a bonus mark based on that. And I think I'm going to put it as high as, I'm not sure, I don't know, something like between 5 and 10%. A bonus of 5 to 10%. That means if you don't attend, you don't lose anything, but you don't get anything either. And I think people need bonuses in math and physics always, right? So the tests aren't that hard, but traditionally when you do a multiple choice true-false test, it's a little bit more difficult than you think it is. It's long. We do 2 hours. At least we do 3 tests in this course. I talked about that as well. Just as a recap, this is our plan. This is our plan for this semester. I like how it jumps around. Let's just make sure it goes a little bigger so you guys can see it. Again, we're starting off with trig, which is what we covered this week. For those people who missed the lecture. And then we're doing a bit of physics in week 4, and then we're doing our first test on week 5. Test is going to be true, false, multiple choice. It'll be in this room, all right, in your labs. Also, there's going to be assignment 1 that I'm going to hand out to you next week. It'll be a group assignment. I recommend that you do it with somebody else, but that you also do your own work. So you do your own work, you understand what to do, and everything else. We can help you with test number 1, right? So assignment 1 is linked to test 1. Assignment 2 is linked to test 2. And after test 1, you don't have to remember anything about trig and calculus. I won't be testing you again on that in test 2. So each test is not cumulative. It's just separate. It's kind of an encapsulated module of its own. And that's how I'm going to be testing you. So these slides are up on Blackboard right now. And then from a weighting perspective, I talked about this. Assignment 1 and test 1 are the lightest combination. So they're like 15 and 15 makes 30. And then you can see that the combination, the tests, test 2 and 3 are weighted a little heavier, just 5% more. And notice there is no space for bonuses. I'm going to give you bonuses based on your attendance and your exercise that you do in class, right? Because I want to be able to give you a fair shot at doing well in this course, all right? All right. So we really talked about this part, geometry and trigonometry, and how it really helps us understand physics. Without trig, physics becomes quite difficult. I mean, you can also use vectors and matrices, but I think we covered things like angles and triangles, and that's what we're going to cover in more detail today. All right, I'm not going to go over all this stuff, but I'm just going to skip down to, just make this a little smaller. I'm going to skip down to the parts we were talking about. We talked about that angles are, just as a review, you know, in a circle, they make up 360 degrees. Each radii of a circle is equal, of course. And typically what we want to do is we want to measure counterclockwise, and we'll talk about that in a bit from a computer perspective. We talked about degrees. We like to measure angles in degrees, but computers like to measure angles in radians, right? Because when you do your programming, you're going to be asked to do stuff in radians. A lot of times your functions will work in radians. How you doing? And here's a good example of adding a bunch of different angles together to make up 360 degrees. Okay, we have a special relationship with perpendicular angles or right angles, 90 degrees, which is what we're going to be using for a lot of the stuff we do in physics, 90-degree angles. And I also talked about briefly how we use a coordinate system when we map stuff, when we graph stuff out. The top right quadrant would be positive, and the top left quadrant would be both negative from a Cartesian perspective. However, one thing to note is that in computer graphics, this may not be the case at all. So if I'm mapping stuff out in computer graphics, going in the upwards direction would be a negative y, right? A lot of times. And it really depends on your coordinate system that you're mapping out. Why? Because when we draw stuff in computer graphics, we draw to the right and we draw down, okay? And so this coordinate system is great from our math or physics Cartesian coordinate system, but we would probably flip this around a little bit when it comes to, like it'd probably be more like this. You kind of flip it across, you know, your y-axis here when it comes to the stuff we do in computer graphics. And you're going to notice that, or maybe it's this way actually, across the x-axis. There we go. Okay, so we talked about that really briefly. And then we talked about kind of naming. So acute angles are the names for angles that are smaller than 90 degrees, and obtuse angles are angles that are greater than 90 degrees. Talked about that really briefly. We also talked about, you know, things like, you know, pi. One of the questions we had was, hey, should I you know, access a library and use the library's pi value, or should I, you know, make it a constant? And my answer is, chances are, you know, the library will have it, but if you don't use a library, like a math library or something, then putting in a value of pi is pretty good. It's in your program. It'll optimize anyway from a C++ perspective, but it's not a bad idea to have pi and the value of kind of a multiplier for radians and degrees. Okay, so this is an equation that really describes the area of a circle. And this is the equation that describes the circumference of a circle. And sometimes we need area and circumference to help us with collision detection, which we'll get to in the latter part of the course. Okay, so nothing too crazy. So it talks about radians here and why we need to convert. Typically what, you know, I recommend is that you have a multiplier to convert degrees to radians, because you're going to need radians for all of your calculations in from a computer perspective anyway. Same thing here. So I'm just skipping through this stuff because we kind of covered it on the lecture, and I want to get to the actual work that we're going to do today. All right, triangles. This is really important. I'm going to make this a little bigger. Naming of triangles and how we use triangles when we describe them in this course, right? Now, typically what I said in the lecture was that you can diagram your triangle any way you like, and that's true. But this is a convention that we use a lot of times when we do if I say angle ABC or triangle ABC, you know, what I really mean is I'm drawing it from the right. So A to the right B and then C. Notice that the B's, the beta, and the small b all line up. That means from here, from the big B, the capital B, all the way through the beta into the small b. If you think about drawing a line, so if I draw a line from here all the way through, you can see that these are all B's. And, you know, at the same time, you know, these are all C's. I'm just drawing a random line here. And these are all A's, right? Which is kind of important to note to figure that out, right? I'm drawing this so that way you understand that when we make relationships, when it comes to triangles, and especially in physics and calculus and all that stuff, that there is a relationship with the angle and the opposite side of the triangle, okay? So these angles and opposite sides, and the naming is important. So when you draw a triangle, if I ask you to draw a triangle next week or something like that, or if I ask you on a test, usually what I recommend when you work out your problems is, again, that you have A, alpha, and then lowercase a, all in one line, all right? Again, we use alpha, beta, gamma. Gamma would be the C for Greek, right? Equivalent in the alphabet. Not really, but you know, that's what we use. And that's how it's done this way. So questions around naming and kind of diagramming a triangle. Here's the thing that I can also tell you is that when we do this, we're just going to do these changes for a second. One of the things is, if I want you to solve a triangle, I want all of these points, first of all, on the triangle, if you can. And the second thing is, I want all the little a, b, and c's, and the alpha, gamma, alpha, beta, and gamma, all to have values. So when I say solve a triangle, it means solve the angles and solve the lengths of the sides, right? It doesn't mean just solve the angles or solve the sides. It means do everything. Okay, that's what it means. Okay, so that's triangles, you know, kind of on a high level, and what they have. Here's an example of another diagram we talked about earlier. And you can notice that there's a relationship when we put this stuff together of different angles. So you see that these angles all here must add up to 180 degrees. So for example, alpha, beta, and gamma, all these three angles add up to 180 degrees. And there's a relationship with kind of complementary angles. So there's an angle here, beta, and it's the same angle over here, okay? And the same angle down here. They're all the same angle, right? So these three betas are all the same, and these three alphas are all the same, and these three gammas are all the same. And it's the way that angles work when you put them inside of a diagram. Okay, so very, very straightforward. Something to note, though, is can we tell what angle alpha and gamma make right now? And the answer is when this diagram, because there's no numbers at all, the answer is no. We have no idea what this is. We have no idea what this is. We can kind of guess, but we don't really have an idea exactly what this angle is going to be because there's nothing marked in the diagram. In fact, this diagram could be drawn wrong. It could be actually skewed more to one side or the other. We don't know. So sometimes people make assumptions that there's an angle that doesn't exist. Different kinds of triangles we talked about as well. We talked about triangles with the same on all three sides, same lengths on all sides. Those are equilateral triangles. Then there's isosceles triangles that have two sides the same, and scalene triangles that have only one, or each side is different, is what I was going to say. It's equilateral, isosceles, and scalene. And these patterns of triangles, again, I talked about this at lecture. Triangles are used to make up any graphic that you make from a CG perspective, from computer graphics. We use triangles or polygons to kind of create some object that you see on the screen. Actually, one of the tests that one of my colleagues would do with some of the first years is say, okay, do me a favor, show me how you draw a triangle with CG from scratch, right? And I was like, don't do it, it's really hard, right? Because, you might think that's easy, but actually using modern GL, it can be quite involved to kind of draw a triangle. All right, so also we have to talk about legs of a triangle. Each side of a triangle is also called a leg. And there's a special leg of a triangle when it comes to a 90-degree triangle called a hypotenuse. Hypotenuse would be the opposite side of the right angle, okay? And that's really important because it has special properties. An example would be, here is a right angle triangle. Notice it's drawn the exact same way, but one thing that's missing is the gamma that's marked on the right triangle, right angle here, next to the C. So right here, next to the C, if we were going to draw it, we'd also draw a gamma angle. But we know what this angle is, right? Whenever you see a square like this, it denotes 90 degrees. You should know that. And we also know then that if this angle gamma, which is not marked, is 90 degrees, then alpha and beta must equal to 90 degrees because that is one of the properties of a triangle. We have all internal angles must equal to 180 degrees in a triangle. Okay? We're going to come back to this diagram in a second. Okay, we're not going to talk too much about Pythagoras. But one of the things that Pythagoras did is he kind of, discovered, Eureka, he kind of discovered that, the hypotenuse, you can calculate the length of the hypotenuse by taking the square root of the squares, the sum of the squares of the other sides, right? And when you do that, you get the exact number, or the length of that side. And he used circles a lot, actually, to figure that out. Circles and everything else, and measurements, and he did a lot of observations. So this is a very common formula that we see. We talked about this on Tuesday as well. This is good for finding out the exact length of a side, but bad to use every single frame to find distance. And the reason why it's bad is because of the square root. Square root is heavy when it comes to computational expense, so it's computationally expensive to do, a square root, especially if you're doing calculating distances between objects and there's many, many of them, like hundreds, right? That would be bad. There must be other ways, more efficient ways of calculating collisions and distances. And a lot of times what we can do is we can use voxels, grids. We can use broad phase collision detection where we say, okay, well, I'm not going to start detecting collisions or distances until the objects get closer. And again, we also talked about how that could also, on a negative, create an imbalance when it comes to performance. So sometimes we have great performance because we're not checking collisions, they're way far away. And then when we get closer, we start checking collisions a lot more, and then performance dips, right? Which we don't want. So sometimes I say to students, it's better to have bad performance all the time than really good performance some of the time, and then it slows down when you're trying to check for collisions. That's kind of a weird thing. And people don't like that when it comes to gameplay. So I wanted to talk about this because we're going to be using Pythagorean theorem today and how to figure out parts of or sides of a triangle. And it's important when it comes to physics. We're going to use Pythagoras and Pythagorean theorem a lot. We got a right angle, and I also talked about last Tuesday, just Tuesday past, there's special triangles, right? There's these magic triangles that have, kind of magical relationships that we can always see. So we know that this is a special triangle, a 3, 4, 5 triangle, right? And we're going to see these magic triangles. Actually, there's 3 really, really common ones that I always want you to remember. 3, 4, 5, 1, 1, root 2, and 1, 2, root 3. Those are the 3, most common ones. They have a special relationship because the angles are always the same, right? So we're going to figure out what these angles are, right? 53.1, I think it is, and 37.9, if I can remember. But these are the angles that we're always going to see, but they all, again, add up to 180 degrees. Okay, and there's other ones. If you look up on Wikipedia, you can see 3, 4, 5, 5, 12, 13, 7, 24, 25. When you see these relationships, sometimes it helps, especially if you're a mathematician. We're not mathematicians. But if you're a mathematician, if you recognize some of these magic triangles, it helps you figure out the lengths and sides. Yes, question? Those are the sides. So each of the sides, so if I say 3, 4, 5, that is 3 for the bottom side, 4 for the side. So the x-axis is the first number, the y-axis is the second number, and then the hypotenuse is the last number. That's how it works, okay? And so these are magic numbers that you can see. If you have a 36 and 37 as an example, this bottom one right here, you're going to get an 85 length for the hypotenuse. That's just how it's going to work out every single time. These are very common magic triangles that we're going to see over and over again. Not just in physics, but in life. They actually naturally occur, okay? Which is interesting. In fact, there's a lot of naturally occurring patterns in math. For example, the Fibonacci sequence we see in nature all the time. And these are one of these kind of things that we see a lot. The ones I want you to remember are 3, 4, 5, 1, 1, root 2, and 1, 2, root 3, okay? However, notice how I said 1, 2, root 3, and I didn't say root 3, 1, 2, right? It's because the way I remembered it. 1, 2, root 3, 1, 1, root 2, okay? But really, if we think about what I said, we should really call this a root 3, 1, 2. but it's just easier to remember the other way. Notice that 1, 1, root 2 always has 45-degree angles. So this is why this is a very common situation, right? When I draw something very symmetrical triangle, it's an isosceles triangle with two sides the same, right? And a right angle, then you know it's going to be 1, 1, root 2. And what I mean by that is the proportions of each side is going to be 1, 1, root 2. So if I had this triangle being 4 times larger, it would be 4, 4, 4, root 2, right? As an example. If it was 10 times larger, it would be 10, 10, 10, root 2, right? And the same thing goes for the other one. It would be, you know, if I was making it 4 times larger, it would be 4, 8, you know, as an example, and then 4, root 3, okay? And 3, 4, 5 triangle, you can multiply it by a scalar again, and you would have the same relationship, and that's what we're talking about. And that's why these triangles are quote-unquote magic triangles, because they're the same, they're very, very, you know, similar every time you see them. The other thing we have to think about is you can find the gradient or the slope of a line by the relationship of rise over run. Now, this is a typical thing we do in math, but sometimes it doesn't work very well in computer graphics. And we'll talk about that a lot when it comes to finding a slope. So a good example of this is the slope of the line is, you know, the relationship of, you know, kind of rise, which is the y value, over x, which is the run, which is the x value. And also a lot of times when we do some stuff with the physics, we'll also see that sine is also always related to the y value, all right, until we actually translate the you know, the graph. And cosine is always related to the x value. Okay, so we're going to see those. And when we're going to use physics starting next week, we're going to see that we're going to take components of a vector. So you can see here there's a vector xy, right? There's actually should be a kind of a, I'll just draw it. Imagine if we had a vector going this way along this axis, right? So there's our vector xy, and of course it's going to, you know, up to xy up here as an example. So we'll draw this back. Here's our vector, and xy has two components. It has the A component, which is on the y-axis, and the B component, which is on the x-axis, okay? So simple stuff. Okay. And we have relationships between these values. Also, what I did last day was talk about a graphing tool that I like to use for visualization called Desmos. So if we bring up Desmos, I also put this on your Slack channel. Please, like I said, please, you know, kind of connect with the Slack channel to see this. Let me just try and put on the sine of x. So here's the sine of x. And this is a great example of, you know, a typical pattern that we're going to see. So we have, you know, notice the sine starts off at 0, right? So this is the beginning of the cycle. And as sine progresses, so every 90 degrees, sine moves, right? So at 0 degrees, sine is the answer is 0. So if I kind of hover over here with Desmos and click in there, you can see it's 0, 0. So when x is 0, y is 0. However, when x is pi over 2, if you think about what that is, if pi is 180 degrees, then pi over 2 is 90 degrees. So sine of 90 then would be 1, okay? And a sine of 180 degrees would be 0. So, and it keeps cycling this way over and over again. And a sine of, you know, 3 pi over 2, right? So that'd be 270, would be -1. And then a sine of 360, again, will go back to 0. Okay? So this is your typical sine wave that we think of. And if you think about this, you can always figure out those values if I give you a number. If I ever give you sine of 90, you know that it's going to be 1 every single time, right? And so instead of trying to figure out what that is, there are some standard values that you can figure out. Some other people also remember the, you know, the halfway marks. So I want to figure out what the kind of the halfway or the 45 degrees, which is somewhere in here. You can figure out what that is, you know, by, you know, what kind of going in here. And this is the great thing about Desmos. You can go through here and figure what that is, right? But it gives you the actual values, right? And these things repeat. So this is sine. And I just want to overlay cosine for a second. Let's take a look at cosine. So cos of x looks like this, right? So here's the difference. Sine starts off, as an example here, this is the red line, and cos starts off here, right? So it doesn't start at the origin. When x is 0, cosine is 1, right? Cosine of 0 is 1, which is kind of different. I'm going to hide the sine thing for a second so you can see that. And you can see how it dips down. So 90 degrees, as an example, here's where it's pi over 2. So 90 degrees, cos of 90 is 0. And then cos of 180 is 1. And then it goes back to cos of 270 is 0. And then cos of 360 is 1. So this is -1 and a 1. And so this is the typical pattern. So the reason why I'm showing you this is we're going to see this over and over again from a mapping perspective, and it'll help you visualize what sine is doing. And why am I showing you this? Well, because we create wavy aliens that come at you. You know, they dip in and out. You know, they have a pattern where there's some kind of formula that they use from a a flight pattern perspective. Or maybe you're going to use some kind of missiles that kind of wave in and out, to hit your target, or they're going to use it against you. Right? There's a lot of ways you can use sine and cosine to make interesting graphical effects. One thing to note is when you use tangent, that's kind of the weird thing. So if I go tan of x, you get this real weird asymptotic kind of graph, right? So the tan of x, if you notice, they kind of spiral to infinity. So they kind of do this asymptotic dance into infinity, which is kind of a neat thing. And there's a relationship with sine and cosine. So if I want to find out sine and cosine or tangent, I can take sine over cosine and I get tangent. Okay, that's the really the a relationship between sine and cosine. The other thing that we're going to talk about a lot is if I have an equation like something like -2, and then if I say something like x plus 3, and then to the power of 2, as an example, and then we add 4 to it as an example, we have this equation of this parabola. So here's the parabola. Okay, we're going to see this effect a lot. Okay, let's take a look at this for a second. So there's values here. Here's this piece, which is some kind of addition to x. We're going to call this a, and we'll make this b. Actually, we'll make this b and c, just to be clear. So there's a, b, and c, and there's also a right here. So we'll say 2a, minus 2a x plus b squared plus c. Right? Here's an example. And if I put these little values on top, so if I make them all sliders, just to see what this looks like, what they do. So let's make them all zeros for a second. So if I make C 0 and I make B 0, keep A as 1 for now. You can see that the parabola starts here, right? Let's make A -1 just for a second, so you can see that what it would look like, -1. So typically this is what a standard parabola would look like. You got this A and it kind of dips out of here, as an example. And if I move the B and the C one way or the other, let's move the B value. So if I move it towards the left, so negative, it moves the whole parabola to the right. Okay, that's just the value. That's the effect that it has from an equation perspective, right? If I move it to the right, it moves the whole thing to the left. It actually translates everything to the left, okay, in this way. Go back to 0. And the same thing with C. C actually moves it up and down. So if I move to the right, you can see that it moves to up. And if I move to the left, it goes down. All right. So this is kind of how the graph works. With A, this is interesting. If I make it more negative, it makes it a little bit more narrow. So it narrows it. And if I make it more positive, it makes it wider, until it flips, because it's going to flip down when A is greater than 0. If it's 0, everything is 0, if you notice, because everything is 0, 0, 0. If I add values to this, all it's going to make is a straight line. Can't see what this does, all right? But you can see the effects of these things and how they affect the, the formula, how they affect the graphing of the formula. So I make this positive. You can see that I narrow this as I go greater, and the same thing goes here. I can narrow this as I go more negative, right? It's a very interesting relationship, and I want you to notice this because one of the things you're going to have to do next week when you start your assignment number 1, and I recommend you start your assignment as soon as you get it, is you're going to have to graph something. It's not because I want you to graph something because you don't know how to graph stuff. Oh, maybe some of you don't. But it's not that. It's because I want you to understand the relationship and what it's going to look like, what the graph is going to physically look like when you draw stuff. How does this help with physics? Helps in a lot of ways. If I want to make a jumping pattern of a character and I want to make him go in kind of like this parabola, a nice parabola, you can make a formula that does that, right? So instead of making like true physics with gravity and everything else, you can kind of create almost like a faux physics where your character has a pattern where he jumps, okay, and lands. All right, so that's graphing in a nutshell. Let's go back. We'll come back to that. Again, I'm really skimming forward here with some of the stuff we're talking about. We also have these trigonometric identities that you should know. I'm going to give you a cheat sheet on your tests. Okay, there's going to be 2 cheat sheets, one for test 1 and one for test 2. Test 3, you're going to have to program something. Okay, that's the way it's going to work. So it's going to be more like a practical test at the end. So again, we talked about this. Test 1, it'll be mostly focused on trig and calculus. And I'm going to give you a cheat sheet that I make for you, and then you can add to it. I'll give it to you ahead of time, right? Now, I talked about this in class, that you can only handwrite anything else you add into it, anything else beyond what I've given you. And please don't make it micro-sized, so you have to bring a kind of a magnifying glass. And don't give your cheat sheets to anybody else. I won't accept it. Your cheat sheet has to be your own. So what it's supposed to do is give you some of the formulas that you need to help you with the test, and perhaps some kind of patterns for calculus that you're going to see over and over again. So the cheat sheet number 1 is going to have both trig and calculus equations on it that I'm going to give you. And chances are that might be enough, and it may not help you in any way either. Because sometimes it's a time thing. You have 2 hours, and you got to answer all these questions. The cheat sheet's just there to help you if you forget something, right? But it's not there for you to look up every single time. If you have to look at the cheat sheet a lot, you're not going to be able to finish the test. It's just not going to happen. So you need to kind of practice. So some of these identities, and again, we can actually describe these identities in more detail. Although, and if you're interested, you can look them up online on how you can actually, kind of solve these identities and so on. I'm not going to do that here. We don't have any time for that kind of stuff because I'm covering all of trigonometry in one day, in 2 hours actually. Right? So there's no way that I can cover all this stuff with you guys. However, there are some relationships, standard relationship with different kinds of trigonometric functions that you can use to kind of, derive the other ones. And sometimes you need to use that in order for you to solve the problem. Okay, again, you have these sine, cosine, and tangent, and you also have arcsine, arccos, and arctan. We're going to use arcsine, arccos, and arctan, or inverse tan, inverse cos, inverse sine, in order for us to find the angles. Okay, I'm going to show you that today. The really important one is the sine rule. We're going to see this a lot. So there's a relationship here. You've got a triangle we want to solve, and you've got a relationship between the side, like I told you, and the angle. So if I have 3 pieces of information of a triangle, I can start solving one of the other pieces. Sometimes you don't have all the information, but I can derive some of that stuff from using this relationship. And I have partial information. Sometimes also I can use another law called the cosine law. And the cosine law is a little bit more complicated, like it says here. But what it does is it extends the Pythagorean theorem, and it's when you don't have, you have b squared and c squared, but you don't have a squared, okay? So then you can derive a squared from b squared and c squared accurately with using the cosine law. And sometimes what happens also, we use the cosine law when we don't exactly have a right angle. And we're going to talk about that later on. Okay. Area of a triangle is, again, half base times height. Again, I'm just going over this really quickly. And this is a really important rule that I'm going to use over the next series of examples. Sohcahtoa. And I like to think about this as Sohcahtoa, right? That's how I remember it a lot of times, right? Sohcahtoa. Sohcahtoa, the reason why we say Sohcahtoa is it's a mnemonic, so that way we can remember the relationships when I want to figure out the angles. I don't know which one I'm going to use as an example. So here's something. Let's suppose that I have the information. I want to find the angle x. Here's the angle x. And I have adjacent and opposite. Which one would I use? Adjacent and opposite. Well, if I look at adjacent and opposite, is there something like that? Adjacent and opposite, here we go, down here. I would use tangent, right? So I can say that tan x, we know, is the relationship between opposite over adjacent, right? And then we have that relationship. Let's say, for example, it was 3 and 4. So if 3 here and 4 here, opposite, 4 over 3, that would be, we take the tangent, tan x is equal to that. And in order for us to find the angle, we need to take the inverse tan. So x then would be the inverse tan of the relationship of opposite over adjacent, okay? And that's how we would find that out. So Sohcahtoa is another tool we have in our toolbox to help us solve triangles. Great. That was the review from Tuesday. Let's get into the actual examples. So some of the first examples that I've got here is, okay, let's map out this function. Okay, so map it out. Now sometimes what I want you to do, I may ask you to map it out by hand, right? So if I'm mapping this thing out by hand, how do I do it? I need to ask you guys this question. I'm going to go back to you guys now. How do I map this thing out by hand? I'm mapping out a relationship, a formula. I'm not going to use Desmos in the beginning. I'm just going to physically map it out by hand. How do I map this out? How do I create the curve, on paper? What do I do? What's the first thing I would do? Huh? I could point points, but I mean, the first thing I would do is probably draw out the, some kind of thing, right? So first thing that I would do is kind of take this, lines, and I was trying to draw some lines here. So let's draw this line. And I would draw, kind of this line. Oops, if I can draw another one. Let's make some lines here. So there's my graph, a very crude graph, right, with no measurements, right? And then I would, like what you said, is kind of think about points. How do I figure this out? Now, there's a couple ways to do this. I could use Excel, right? So I could kind of put this in an Excel diagram or Excel sheet. Let's open up Excel. And again, Excel will do your graphing for you too. We don't want that. If we want you to try to do graphing on your own, I'm just going to adjust this thing so you can see it, make this really big. So let's say 20. And what I want is the value of x and the kind of resulting value of y, okay, x and y, and then the formula. And if you notice, the formula is x squared plus 4x minus 4 in Excel, x squared, plus 4x minus 4 is what I want to write here so I can remember what it is, right? And then I want to kind of graph it out. I'm just going to kind of make this a little bigger. And let's just do one of these. I'll add some borders. And we'll make them kind of like this. There we go. And I'll really zoom in there so you guys can see this stuff a little bit more. And then, okay, so I want to find the value. I usually start with a value like 0, okay? That's me. And I kind of go down the line. 1, 2, 3, I kind of make values of, values of x. And I put them in here, and then I kind of figure out the value of y. Again, Excel can help you and calculate the result, but let's just do it by hand, as if you don't have Excel or you don't have a calculator. So how do we figure out 0? Well, 0 to the power of 2 is 0, plus 0 is minus 4. So the first point would be minus 4. Okay, so 0x minus 4y. Okay, make sense? And I would fill in the rest of the values. So 1 to the power of 2 is 1, plus 4 times 1 is 1. So 1 plus 4 is 5, minus 4, right, would be minus 1, would it not? Or sorry, 1. Total value. Does that make sense? Right, x squared, so 1 to the power of 2 is 1. Plus anything, 1 to the power of anything is 1, right? Plus 4 times 1 is 4. So 1 plus 4 is 5, minus 4, 1, right? So 1, 1. And then again, if I was going to go 2 to the power of 2 is 4. 4 times 2 is 8. 4 and 8 is 12. Minus 4 is 8. So that would be the next value. And then again, solid values. So 3. 3 to the power of 2 is 9. 3 times 4 is 12. 9 and 12 is 21. Minus 4 is 17. So that would be the next value. And 4 times 2, 4 to the power of 2 is 16. 4 times 4 is 16. That's 32. Minus 4 is 28. That'd be the next value. Let's just do those 4 points. So I've got like 4 points here. Who cares about this one? And now I've got my plot points. These are the plot points that I'm going to use to plot out the my graph. So 0 minus 4. So again, if I was going to go do here. And again, I'm doing this exercise with you so you understand what I would do if I was to draw out this thing. So here's the couple points here. Now again, please forgive me. I'm going to try and make a crude graph without measuring. Right, so let's say this is 4. And this would be minus 4, so we're just going to put a minus 4 in there. yeah, this is where the problem starts. So I'm going to use a text box and put it over here. This will be -4. -4. It's massive. A massive -4, which we're going to reduce to like, I don't know, 8 points or 6 points. This is -4. And we can see that this would be -4. Right? And so the first point, if I'm going to plot this out, let's just get a little circle there. Here's a circle. And let's make that circle a little bigger so we can actually do something with it. Bear with me while I do that. ARG format. Yeah. Let's make that circle a black circle. There we go. Sure. And let us go in there a little bit more. It's a little bit smaller than that. There we go. And what I want to do is I want to try and plot this out. This is my first point, my first plot point. And then I would do the next one, right? So kind of go to the next one. And you can see that it's 1, 1. So again, I'd have to draw a line this way. And these are really big lines, probably way too big, but that's okay. So kind of draw this line there. And maybe do another one. There we go. And I want to grab this point here that I just made. And I want to move that to here. So that's be the next point, right? And that would be the first, that would be, 1, actually 1 and 1 if I'm not wrong. So 1 and 1. So let's make another one of these. Come over here. Again, it's just rough. So 1 and 1 would be somewhere here. And you can see how I'm going to start making the graph. And then 2 and 8. So 2 and then 8 up. So let's just grab a bunch of these. 3, 4, 5, 6. All right, guys, I know this is painstaking. 7, and 1 more. And then these are the only points I'm going to draw, okay? And we'll make this, we'll extend this line a little bit more. So see it. If there's 8, and then 2 and 8 will be up here. So let's just grab one of these dots and draw that point up here. So there we go. We get another point, right? So approximately there. So you can see that the curve would look something like this. Okay. Anyone have questions around that? And if we were to map this with Desmos, right? Let's go back to Desmos and map that out. So I'm going to grab all these points. Okay. And then if you want to do that, I'm showing you Desmos. I think it's a good tool from a graphing perspective to figure that out. So x squared plus 4x minus 4. Squared plus 4x minus 4. X squared plus 4x minus 4. You can see that that's the graph. And if I zoom in here, you'll see that pretty much is exactly what we've graphed is what it is. Okay, minus 4, and then this is slightly different. Make sense? So that's the graph that we're looking at. Okay, and again, if I was to make, if I wanted to translate this to the right, as an example, or up. For up, I would just change this value. If I want to make this move up, I could change this to like, 2. You see that would move up. And if I wanted to move this to the left, then I would put this in brackets, or left to right. So I can put this in brackets, this kind of part for x. Oops, if I can actually do this properly. All right, just examples with graphs. I want to move it to the left, then I would add a value to this, like plus 3. Over to the left. If I want to make it plus 4, more to the left. Right? It's up. What's happening right now? Oh, because we're not in the square root. We're moving it up this way as well. Actually, all this part outside of the square root is moving it, or the square is moving it to the up direction. Right? Let's undo that. And what I meant to do, of course, is do this. So if I wanted to say x squared, so up here, instead of doing this, I could say x squared. It's just easier to do it again. X, if I put the power of 2, that's the same thing. But if I put a value in here, like plus 5, you can see that that would be translating it to the left. And if I made it a minus 5, so minus 5 would translate it to the right and up. All right, so there we go. So that's how the relationships of graph works and how you graph the stuff out. Okay, so that would be the first question that I covered, right? Let's just graph the following function and confirm with Desmos. You're going to get a graphing thing on your assignment, like I said, okay? Next, let's go to the next one. So this is another one. I'll leave this one for you. I want you to try this out on your own. So try mapping it out by hand if you can, as a good exercise to see how that looks like. Again, guys, please forgive me if you've done this stuff like a ton of time in high school, or even this is kind of like grade 4 stuff, right? Yeah, forgive me in a great deal, but some people have forgotten. They don't know the relationships of graphs, haven't done this for a long, long time. And we're going to see this kind of stuff over and over again when it comes to physics. And then I'm going to say, recall that, blah, blah, blah. And you're going to go, now, Tom, I don't recall a damn thing, right? And so this is a way of you getting to recall some of this stuff again. I'm kind of unhazing some of this hazy stuff that you have in your deepest memories, okay? For some of you. Some of you have never learned it. All right, now here's something. Here's a question that I want you to help me solve. So I want to look to solve x for example A. All right, how do I do that? What approach do I take to solve x? Anybody? Yeah. Yeah? Excellent. So the answer is, and I got to repeat this because people are watching maybe live or I'm recording this for somebody else. Since I know that this little square means a right angle, that means that 2x plus 3x must equal to 90 degrees, right? So let's just jot that out. And again, one thing to note is when you make your paper, your assignment number 1 for me, there's 2 ways to hand it in. You can write it up by hand, take a picture of it, and make it a PDF, right? That's one way to do it. Or you can use PowerPoint or Word or some kind of Microsoft or other product. And when you do PowerPoint or Word, you can use the insert function to insert an equation, and it'll actually nicely print it out, okay? But sometimes what happens is if I use an equation with Microsoft Word or PowerPoint, it shifts things around and doesn't give you control. The way to abate that is to use a text box. So I use text box, and let's say I want to make a text box that's right here, right? And then in my text box, I also insert an equation. This gives me full control over where I can set my stuff up, right? So I want to make that equation in here, and I'm going to say something like, so 2x, plus 3x is equal to 90. That's the equation, right, that I'm using here. Why is that? Again, because these angles here, 2x and 3x, equal to 90 degrees, because that's the angles that we're seeing. And if I was going to solve for this, it's just really like a little bit of algebra to do this. Very simple algebra, actually. I'm just going to kind of copy paste here. And where, I want to isolate this, so let's make this 5x. So that's the next step. Okay, 5x is equal to 90. And we know then that x is equal to 90 divided by 5. And again, to do this properly, I'm going to go back into insert. I'm going to go back into pi and 90 over 5. You can use this little fraction part here, so 90 over 5. So I can actually type this in nicely. So it'll look like a formula, 90 over 5, which I don't want to do more than one line here, but I kind of did that earlier. 90 over 5 is equal to, what, 18, right? Again, I have control with the text box. I can put this kind of directly underneath these things so it looks kind of nice. If you really want to do it right, it should look kind of like this, with all the equal signs kind of on top of each other as much as possible, right? So you know that x is equal to 18. If that works, let's check this out. So 2 times x is 36, and the remainder, 54, 36 and 54 is equal to 90. And those are the angles that we want to find. That's one way to solve it. Okay, cool. So we did this one. How do we do this one? What's the difference? And don't answer. You got you in the back because you kind of had it. Anyone else want to try and help me solve this one? Is it the same thing here? Do I do the same thing? Yes. Yay, people are awake. Yes, it's 180 degrees instead of 90. So you take the same thing, 7x plus 2x is equal to 180, and then you can solve for x, right, to find out what that angle is. I'll let you guys do that on your own. Okay, not that it's too exciting. Why am I showing you this stuff? Because a lot of times students forget that that's the relationship. You're like, duh, I can't figure out the angle here. I don't know what it is. Well, you know that if you have some kind of variable like this, right, x, and you have this information, a relationship between one and the other, an angle and the other. Like if one angle is 7 times larger than the other one, but they both must equal to 180 degrees, what are they? And sometimes you'll get an answer like question like that. One of the angles is 7 times larger than the other one, on a plane that's 180 degrees. Solve for the angle. What's the angle that we're talking about? And it'll be written out, and you'll be like, okay, I understand how to do algebra, but I can never solve problems. Problems like confuse me, right? a lot of times it, kind of some questions you might see on tests or whatever might try and hide the answer. I'm not going to do that with you guys. Two things I'm going to promise you. One, I'm not going to give you triangles you cannot solve. Okay? I'm not going to sit there and go like, here's a triangle, solve the triangle. And then A, B, C, D, or E. And E is like, there's no solution for the triangle. If you ever see no solution on the triangle, that is not the answer. I'm telling you in advance. I'm not going to do that to you. Okay? There will always be a solution for the triangle. Okay? Because out of that, the stuff that we're doing here is very just a review. It's just trying to get you to understand relationships more than anything else. Okay, here's something. Help me out here. How do I solve this one? So I want to find sine, cosine, and tangent values for angles A, B, and just A and B. Let's start with A. So if I wanted to find the relationship, actually the angle here would be alpha. That's the angle I want to find. Okay, so if I have a triangle ABC, I want to find the angles for alpha and beta. Okay, so again, what you can do here is I can insert equations for that kind of stuff. If I want to find, in here, this is also the Greek letters. So if I want to find alpha, this is the angle I'm actually looking for right here, alpha. And I can kind of copy paste that. And down here will be beta, right? Beta looks like a bee with a funky tail, right? When I was learning Greek back when I was a kid, it was the most difficult and annoying thing. I'm like, I drew a bee. Nope. Teacher would say, nope. I'm like, why? Right? It's a bee. It's not a bee. It's beta. And actually in Greek, you don't pronounce it beta. You pronounce it vita, right? Of course, because it's Greek, right? Doesn't make sense. Anyway, so we have alpha and beta, and these angles are the ones we want to find, right? So how do I find angle alpha? What steps would I take to find that? Do I have enough information to figure it out? That's the first question I have to ask you. Okay, some of you are nodding yes. Okay, so tell me steps. Give me steps, guys. This is your stuff. Next week, I'm going to give you these examples like this in a little quiz or exercise, and you're going to have to hand them in. So pull out your pencils and papers. Help me out. How do I figure this first out? What's the first step that I would do? Yes. Okay, well, first of all, let's say I'm solving for sine. I want to find the sine of alpha. How do I do that? Okay, good. So I'm using Sohcahtoa. That's the way you solve this stuff out. So I'm going to insert Sohcahtoa, right? I'm going to insert a text box here. Actually, I'll insert it over here. There we go. Sometimes you got to insert it off the path here, and I'll insert sig. I'm inserting sig. Sohcahtoa. Okay, and I'm going to put this kind of on a line. So this is just a mnemonic. I'll put it over here so you guys remember this. Maybe up here somewhere. Sohcahtoa. So I'm giving myself some room. So again, I want to find sine. I got to take opposite over hypotenuse. Okay, so here's this. What's the opposite of the alpha? Let's go. Yeah, so 36, because this little a over here would be 36, right? So I would take 36 over the hypotenuse. Which one's the hypotenuse? Anything opposite the 90-degree angle is the answer, right? So 85. So 36 over 85. So the formula would look something like this. I'm just going to do one with you, okay? Not because I want to annoy you or anything. So again, I'm going to insert a new text box here, right? And inside the text box, I'm going to insert an equation. We're going to type out, again, it's going to be the sine of alpha, right? Is going to be opposite over hypotenuse. I'm just going to put the values, right, for now. We know that the opposite is 36. Oops, let's just actually do one of these. So 36 over 85. How did I get that? I'm using Sohcahtoa, right? So opposite over hypotenuse, sine, right? So that is what we start off with. There we go. So that's the first part. Okay, and can someone tell me what 36 over 85 is? The number, please. That's important to know. Anyone figure that out for me with a calculator? And we'll just kind of delete that whole thing. There we go. Numbers. 0. What? Okay, it's a big number. Should I keep all those digits when I'm doing my calculation to figure out what alpha is? What's your thoughts on this one? Should I shorten should I truncate now? Should I round now? Why no? Why no? No is the right answer, all right? Why is it no? And you'll get an answer. You'll mess up in your test if you don't do what I'm telling you here. If you round now before you try and get the angle, your angle will be slightly off, right? You'll get a rounding error. Okay, you don't want to round now. You want to round after you get your angle. And sometimes I'll tell you something like round to 2 decimal places. Not here. Your final answer. Okay, cool. I have sine alpha is equal to 0.42352941, which is what you gave me. Okay. How do I figure out what alpha is now? I need to take the inverse sine. Okay, so copy paste. So it's not this, it's alpha. Let's do this. I'll put in alpha. Where is it here? Format, insert equation, and I want to go alpha. Alpha is not this. Alpha is the inverse sine. And actually what I'll do is I'll put in that inverse sine stuff. So the inverse sine, you can say, sine to the -1. That's how it's usually written. Of all this. That's what alpha is. Okay? Why would that be? Why would alpha be the inverse sine? Can anyone figure that out? Like, can everyone? I'm writing this out for you because you're going to get to this. You're going to say, I got this weird number. It's like 0.4 something, and he's looking for an angle. You haven't taken it far enough. If you stop here, this is not enough, right? Because we know that sine is alpha, there's an inverse relationship to try and find out what alpha is, and we use inverse sine for that. That's the simple answer. So what is that? If you take the inverse sine of alpha? Just a moment. You're too fast for me. So much I kind of get this out here, and we'll write this down. What is it? Sorry? 25.055. Keep going. So it's 25.055. 755. Okay, I say I want to go to 2 decimal places. What's the real answer? What do I want? What should it be? Correct, because 7 would make this 6, or 5 would make this 6 as well. I round up for 5. So all this would be gone, and it'd be like this, right? And that would be the answer. If your numbers are correct, I'm not sure, I haven't checked your numbers. If your numbers are correct, then that would be the answer for the angle of alpha. Okay, if we know alpha is 25.06, what's beta? Is it 180? No, it's 90, right? Minus 90 minus, so what is it? 74.94, right? So that we know what beta is automatically, right? Because we can calculate, because we know the properties of a triangle, right? So we know then that beta, here it is, design, beta, here's beta. We know that beta then is 74, it's not quite 74? Someone said 74.94, yeah, that's what I was going, 74, what the heck? 64.94. If your numbers are correct, if what you've given me is correct, then based on what we've been given, alpha is 25.06 and beta is 64.94, if what you've given me is correct, which I haven't checked. So why would I do this? I did this for the sine of alpha. Once I find the sine of alpha, I can solve the triangle for everything. And I can give, usually what this question is asking for is, show me the relationship, show me the this part here. This would be enough. If I asked you for the sine of alpha, I would probably stop you here, up here, like with this stuff. I don't need you to solve everything. But, however, if I said, give me alpha, give me beta, the actual angles, right? That's a whole different thing, right? Sine of alpha could also be taken this far, to 0.42, something like this. If I said, take it this far to the decimal point, and within 2 decimal points, if I said that, then you would take this number here, and then you would round, if I want you to stop there. But if I said, give me alpha, the angle alpha, then I would take you down to this, right, 25.06, okay? So depending on what I'm asking for. Again, we can use cosine and tangent as well So to find cosine, it would be adjacent over a hypotenuse. The adjacent angle is this one, 77. Hypotenuse would be 85. To find tangent, it would be opposite, as an example. So the opposite angle, 36, over adjacent, 77. Okay? And that's how we would use that. So Sohcahtoa is definitely a really interesting and valuable tool for us. Here's another thing. Could I use, instead of Sohcahtoa here, could I use the sine rule to figure things out? Kind of, right? I can probably find the sine rule and figure that out as well for the sine. If I wanted to find the angles, for sure, if I want to solve the triangle. All right, here's one. And this is one where we're going to get more obtuse. We're going to get more, people get angry when you see this kind of stuff. You're like, wait a minute, what does he want? What do I do first here? Solve a right angle triangle ABC if little a is equal to 44.25 centimeters and little b is equal to 55.87 centimeters. What do I do first? First things first. Draw the damn triangle, right? Because if you don't draw the triangle, you know what's going to happen. You're going to be like, well, I don't know, right? Draw it and label it. So the first thing we want to do is draw the triangle. Now, again, there's many ways to draw this thing, right? See if this actually helps me out to draw the triangle or not. Not. If it's a right angle triangle, we're just going to draw it on our own. Yeah, so we want to draw a right angle triangle with the long side here, right? So that would be, this one, and then kind of like a long side over here, and then let's see if I've probably drawn it too off, but I want to try and draw this triangle this way. There we go. There's my triangle. I know that I want to draw the right angle symbol, which is the little box, right? So this is a little box I'm going to draw here on the corner. And again, I'm drawing this like this so that way people who are watching online can see it, not because I can't draw by hand, right? And I want to start labeling stuff. Okay, so cool. So if we went with convention, the first thing that I would do again is I would insert, kind of a text box. And again, I recommend text boxes, guys, because just more control. So capital A as an example. And then if you're going to do it with a program like this, and then I'm just going to copy paste. B would be down here, right? When we make the angle, there's B. And then C would be over here. Okay, typically that's how we do it. Okay, A, B, C. And then we draw the other angles out. So little a, and B. Okay, so let's do that. So little a would be over here. So again, I would take this one, copy paste. Little a, and then you just put that out, 44.25, right? That's the information we have. Let's make sure that's a little a, not a big A. And again, we want to do B, which is this one. B would be the opposite of where B is over here, right? So, okay, cool. We're going to put this over here. And B is equal to 55.87. 55.87. There we go. Excellent. And we don't know what C is. Okay, but it says solve the right triangle. Next steps, what do we do? Yeah.
So does C have to be right angle?
Not really. It doesn't matter how you draw it. That's the answer. That's a good question. The answer is it doesn't really matter, right? It matters how you draw it, right? It matters how you draw it. The relationship between the sides, it's going to be the same, however you draw it. However, when I see this, when I see solve right angle triangle, ABC, right? My thoughts are it looks like this. Some other people might also label it differently, ABC, right? But at the end of the day, the relationships between these two sides isn't going to mess up the hypotenuse, right?
Aren't you going to do the slope, right?
It doesn't matter. At the end of the day, when you get the final, I can do slope, but I could do Pythagorean theorem here, which is one of the options. So there's lots of ways to solve this thing, right? So one is you can use slope. The other one is I can use Pythagorean theorem. So, okay, but Pythagorean theorem is messed up here. Well, not really, right? Because it says a squared, ABC, right? So a squared plus b squared is equal to c squared, right? And then I would figure out that that's one of the things. I could also use sine law, right? Sine law is the other thing I can use. Why can I use sine law? Well, because I know the gamma, which is next to the c, is 90 degrees. So I have one angle and I have two sides. I can find out the other information. Okay? So sine law would be the easiest way to figure out. You're like what you said, gradient, right? But I could use, Pythagorean theorem to figure this out as well. Okay, so that's the first thing. So I'd figure out the side. That's the first thing I would do. Once I have this side, right, the hypotenuse, then I have enough information to figure out the other angles, and I can use sine law for that. So you can use a combination of sine law 1 or 2 times, or Pythagorean theorem to figure it out. Any questions around this? So when you get a question like this on a test, right, as an example, I would go through it and I would look for the right values, right? But the angle could be flipped. This triangle could be like this way, right? Or whatever, you could flip it the other way. Depending on how you draw it, as long as the values are correct, you're going to get the same answer, right? And the relationships that you're using. But if you draw it weird, like if I put my hypotenuse somehow, then you're going to get messed up, right? Okay, so let's continue solving this just to go through the exercise. So I want to find what little c is. Okay, so let's go through the exercise for people who don't know how to do that stuff or figure it out, because I need to, this is the tutorial, so the lab, if you will. So what is c? How do I figure out c? Can someone help me out? Which one do you want to use? Do you want to use Pythagorean theorem? Do you want to use sine law? What do you want to use? Since you're talking, I might as well keep getting, going with you. Go on. What do you want to use? What's your favorite method? Do you have a favorite? Or do you hate it all?
I would just do slope.
Slope, okay. So you're going to take rise over run.
Wouldn't that be the basic statement?
It's exactly what sine law is. Sine law, slope gradient comes from the sine law, if you think about it, right? I have to use a sine something anyway. I can't just use slope, right? So sine law is the way to go if you wanted to. And again, sine law says that I need the relationships between, an angle, as an example, and the side, right? So if I was going to draw it out, again, let me just draw out I'm going to insert a text box. Here's my text box. And I'm going to draw out the sine law. So it'd be like, I'm going to insert a formula. I'm going to drag it in there, over there in a second. And let's say, for example, I'm going to have this one kind of equals to a relationship with another one. It's a relationship. It's a model where the proportions of the sides and the angles have a relationship together, right? So I'm going to put the information on the left side that I don't know to help me out. So I'm going to say, well, I want to find out what C is, right, as an example. And I know that I have, the angle is sine of, and we don't have gamma, but I'm going to put it in there anyway. Sine of gamma, right? So that's sine of gamma. I want to find this out here. I don't know what C is, but I do know 55.87, right? And this is, you can use slope, but stuff that I don't know, right? I could say that, actually, in this particular case, that would be the wrong thing to do if I use sine law, because I don't know the angles at all. Usually you need another angle. I have one angle. If I wanted to find the angle, that would be cool, right? But I don't know the other angle. So that would be probably negative. If I want to use slope like, again, 55.87 over 44.25, that's a relationship, right? I could use Sohcahtoa from that perspective. That's one way of doing it, right? So because I want to find the kind of a tangent or whatever. So sine law in this particular case may not be the right thing to do first. Let's use the longer way of doing it. Let's use Pythagorean theorem, just for people who don't know. So it's c squared. Let's see if I can do this properly. Sorry, I just want to confuse anybody. And when I started drawing it out, I was like, probably wouldn't want to show that yet. All right, so it would be like this. So c squared, oops, c squared. And then it's equal to a squared. Sorry, I'm just trying to make this map out properly. A squared, and then plus b squared. Okay, that's the relationship of Pythagorean theorem. And then I know the next step, you could write it this way, or you could write it with the square root. So I'm just going to take it over here. And really what I want to do here is, I'm going to kind of cut this out for a second. I want to use the square root. So insert. And I want to use the square root here. And copy that in. There's a squared plus b squared, right? And this would be not c squared, but actually c, right? With the next step. And then the next step after that, I'm just writing out formulas right now, is to fill in the blanks with the stuff that we know, right? So I would kind of put this down here, and you could say that, well, A is 44.25. Can you give me the numbers, please? I'm not going to put it in here, but can you give me 44.25 squared? It's going to be big numbers. I'm going to make this a little bigger. Again, I'm doing this longhand because some people will round, and you're going to get rounding errors, and that's not a thing we want, right? So you want to take it to as big a number as you can. So the number for a squared is, anyone? Or do I have to do it myself? 1,958. Okay, and the b, what's b squared? Okay, big numbers, right? Again, I'm going to ask you the question, which should be no, right? The answer should be no. Do I want to round here? And the answer should be always no, do not round, okay? Because if you round, you'll get rounding errors. It won't work, okay? And then we're just going to copy paste this. Actually, yeah, we'll do that. And I want the answer for this whole thing here. What is C then? If C is the square root of this, what do I get for C? Round it to 2 decimal places, please.
5075.
What? Square root of that, right? What is that? 71.27. That's a really long way of doing it, right? What the other thing I could have done? I mean, I wanted to show you this way because sometimes, you know, you're stuck. You don't remember what to do, and you know, you want to find the answer and you want to verify your answer. And so we've got a value 71.27 for C. Okay. Okay. Now I can use, for sure, I can use sine law, right, to find the other angles, right, and use that sine law where I take, you know, 71.27 over 90 is equal to, you know, something over 55.87 to get, you know, angle beta as an example, okay, and so on. I'm not going to go through this with you. I recommend you go through it and figure it out, like actually try the example out on your own, solve the triangle as part of your homework. Remember, next week, I'm going to present the examples. I'm going to let you do it, and I'm going to help you finish it, okay, for your exercise. So there'll be some exercise questions. I'll go over the first part with you, and the second part is your thing to do, okay? All right, cool. Any questions around so far the stuff we've covered? Very simple, very high level, Pythagorean theorem. At least I think it's simple. Some students are like, you think it's simple, but for me, this is like, it's 8 o'clock in the morning on a Friday. I want to get coffee. I want to play my video game. I want to do something, right? Okay, here's where it gets a little bit more tricky. Okay, this is tricky, all right? So please don't take it as tricky. What do I mean by elevation? So it says the angle of elevation from a point on the ground 15.5 meters from the base of a tree to the top of is 60.4 degrees, right? What do I mean by elevation in this particular case? How do I draw this one out? I need to draw this out first, right? So what would the first thing I do? Yeah, you could, yeah. I would draw the tree. I mean, I don't have a tree drawing here, but maybe I do, but I'm not sure that I can draw it too faithfully. But imagine that is, I'm just trying to figure out if there's something that I can, a snippet that I can kind of drag and drop without me having to draw a tree with PowerPoint. That would be very bad. Yeah, there's nothing here. So let's find a picture of a tree on the internet. All right, so doesn't matter. Say tree. Yay. Okay, I'm really lazy. I'll grab this tree. This is a good tree. And I'll save this image as tree. There we go. Tree.jpg. Oops, did I make this wrong? JPEG. Actually, it was already a JPEG. And I'll put this on my desktop, and I'll drag it on. There we go. Tree, desktop, save. And I'll go to my desktop for a second, and I will find the tree. There's my tree. And I will copy the tree and see if it works. And if I'll go back to my PowerPoint diagram and paste the tree. Yay, there's the tree. Cool. The first thing you do is draw your tree out. I've cheated. I didn't draw it. I got a picture of it. That would be okay too. If on an assignment, if you got a picture of a tree and put it in there, I'm good with that, right? All right, so I've got a tree. It says the elevation from the point of the ground, 15.5 meters from the base of a tree. Okay, so let's make this tree a little bigger so we can see what it is. And, you know, sometimes what I like to do when I actually have an image like this, again, is if I go to format picture. On the right, you can see that there are some options for you guys, reflections and glow and all this kind of stuff, and artistic effects. I want to see if there is a way of, I don't know if PowerPoint has that kind of thing. It has fills and lines. I want to kind of fade it out. So there's the shadow effects. I know this is a waste of time. Transparency. That's a shadow, that's a reflection, and a glow. Yeah, there's nothing like that. So I don't know. Or maybe artistic effects. Is there artistic effect? An effect. Okay, I accept that. That's fine. I was actually really hoping for something else, but I really wanted transparency, but that's okay. There's probably something here for transparency. I just don't remember where it is. All right, and then normally I use a drawing program for this, but this is cool because it kind of fades it out, makes it look like a tree. I'll make different lines when I insert the lines in here for my triangle. Okay, so let's go and add in a, go to lines. I want to draw the tree, right? So let's see if I can do this too without taking too much of your valuable time. Let's do a different color, red. Sure, and shape outline and red. Yeah. Good. And I want to, what? And I want to do one of these. I don't think it's going to give me what I want, but I want to draw a line in here, right? Oh, I see what it did. Not what I wanted. All right, whatever. So I kind of want to draw the tree. So basically, I want to draw the top of the tree. This is what it's asking for. And this is kind of weird to see, right? See if I can modify the line, make it a solid line that is red, so you can see it, and maybe a little bit thicker. There we go. And I'll make another one. So make another line on the base of the tree over here, right? And we'll do that same thing. We'll make that line red as well. Keep it and make it a red triangle and fill that up too. And we'll also draw the third line, which kind of goes from here. Now, this is not exactly accurate because I'm trying to draw it here with PowerPoint, but please forgive me. I'm not trying to make it so it's inaccurate for you guys. And let's assume that the base of the tree actually is like that, okay? Just to make it more accurate. And let's just take this line here and make it red just for completeness, not because I really care. There we go. Phew, triangle. So what it's asking for is 15.5 meters from the base of the tree. Now, I know this is the right angle, so I'm going to draw my right angle in there as well. And I'm just going to be lazy and just draw a box. There's a box. That's the right angle. And let's make the fill and all that stuff no fill. And we'll make the line red. And we'll make that a bigger, thicker line. There we go, to kind of match with the box. There we go. Excellent. There's my angle. It's my angle. And I need this side right here, which says it's 15.5 meters from the base of the tree, which means down here, 15.5 meters this way. So this would be which number? A, B, if I was going to label my triangle C, so this would be little a. Okay, so again, I would go to Insert. I would go to Text Box and insert an A. We'll say A. A is equal to 15.5 meters. And again, you can put meters if you want. For now, I don't care if it just says 15.5. There it is, 15.5. And now the elevation is the angle upwards, all right, which is this angle right here, right? This is the elevation. And this would be, if I was going to mark this A, B, C, like this would be angle beta, all right? So again, I'm going to insert text box over here, and I'm going to insert in that text box an equation, which we're going to use beta for. All right, so beta, there we go. I'm going to take that thing there and put it here. So beta is what we have, and we know that beta, beta, I start over here, is equal to 60.4 degrees. That's what beta is, okay? And it says find the height of the tree. So what I'm really looking for is A, B, C, right? B is what I'm looking for, right? Side B. So if I want to put that in there, again, I'm going to insert a little text box over here, make a B, like lowercase b, and take this thing. Now, if it's not visible, you can change the color, which I'm going to do right now. So I'm going to change it to red, and maybe give it a background. Background, solid fill. We'll make it, okay, sure. We'll give it a little bit of white. There we go. All right, so there it is. So beta, B, and then there's the tree. I've drawn it out. And if you were going to get a problem like this in your assignment, you draw your stuff, you label it as best you can. I want to find what B is. What steps would I take? We've kind of done this, but the first part, and I know this is, please don't be bored too much by this, right? We're doing the same things over and over again, right? That's what I'm doing. I'm kind of calculating the same things with what I have, right? So first of all, what do I know? I know that I have beta, 60.4 degrees. I know that I have alpha, right, as an example. I know that I have alpha. And I want B, okay? So what could I do? What can I do to get that information? What information do I have? I have, if I look at B, right? This is what I have. I have beta, right? And I know that beta itself, if I wanted to find it out, would be, I could use opposite over adjacent, right? So tan of beta is equal to opposite over adjacent, okay? That's Sohcahtoa again, okay? So I could drag that out. I can kind of draw this out. So this is the first step that I would take. Now you might take different steps, but I would say something like tan of beta, and which is 60.4. That's what that would be. The tan of beta is actually equal to opposite, which is B. Let's just drag this out here. So insert an equation. We'll do this, and we'll say that it is B over A, which is 15.5, right? 15.5. There we go. Okay. So now I want to solve for B, right? So I cross multiply. So I kind of move this over here, right? So B is equal to 15.5 times tan of 60.4, right? That's the next step. Right. So I want to isolate for B. So B is equal to 15.5, and I'll put times x, let's say, we'll use times the tan of 60.4, okay? And then that's B, that's the side, that's what I would do, Sohcahtoa, right? Does that make sense for you guys, right? The last question, I'm not going to go through too much more difficult than that to get you guys the answer. The other question is this one. Okay. So again, what would I do here? Take a look at the question. Find the angle of depression from the top of a 29.5 meter building to the base of a building across the street located 12.8 meters away. They see this question and they're like, I can solve equations, but I can't figure out problems, right? What do I do here? First thing. Okay, how about the girl that came in late? That's you in the front. Yeah, what do you first do? What's the first thing you do? I know, I'm putting you on the spot. There's no one safe. No one's safe, right? Go, tell me. What's the first thing you would do in this question? Draw it out, right? I would draw the buildings. Okay, I would draw the buildings, not the tree. There's no tree here, right? So, and I could draw crude buildings because they're kind of rectangular. So let's say I would draw one building here. This is the first building I would draw. And then I would draw the second building, right? So there we go, 2 buildings. Okay, so if I have 2 buildings, let's make it more square-ish in the middle. So I've got 2 buildings, and it says, I want to find the angle of depression from the top of a 29.5 meter building. Okay. So I know that this here is 29.5 meters. That's what it's telling me, right? So I'm going to get kind of a triangle here again. I'm going to draw on top of the building so you can see it. I'll draw another color. So again, I'm going to kind of draw one of these. All right, there's my number. I want to go to fill, and I'm going to go into my line. I'm going to make this red so you can see it and make it a little bit thicker. Okay, this is 29.5 meters. To the base of the building, the angle of depression, and the building base is 12.8 meters away. Okay, this doesn't really look 12.8 meters away, but it doesn't matter. Okay, as long as you draw the diagram, if the numbers make sense, that's the most important thing. So I'm going to drag another line to here, right? There's the base of the building, right? And I'm going to drag this to this here and increase the width. There we go. And I want to draw the angle of depression, right? So going back home, the angle of depression, all right? So from the top, and it usually means this. I'm going to draw this line here, all the way down to here. And I'm going to draw this other line. It's almost like I'm drawing a box, right? Here's my other line up here. So this is the angle of depression up here. Not this part. Because from the top, I'm getting the angle of depression. This is where people get confused, okay? I've actually got two triangles here, right? So I want you to help me out here. Here's my solid line. Let's make this red as well. I want you to help me out. What I'm really looking for is this angle right here. I'm going to kind of insert that so I can show you what I'm looking for. So I'm going to insert an equation, and we'll make it so that it is, I'm just using an arbitrary value. We'll call it beta. Okay. Here's beta. I want to find this beta angle. All right. How do I do it? It's outside of the triangle, man. Well, now I'm in trouble, right? Am I in trouble? Okay. What's the way to solve this? Okay, the girl in the front, what's your name? Huh?
Elsa.
Elsa?
Yeah.
Oh, Elsa, you're recorded for history on YouTube right now. Elsa, right? Tell me, how do I solve this triangle? What's the first thing I want? First of all, do I have all my information mapped out yet? No. I need to put the values, right? So I need to put the values down in here. So the next thing I would do is I'll go into insert. Again, I would insert a text box, and I would insert it down over here. Actually, I want to put also the right angle. Let's do the right angle first after the text box. So this would be little a, right? And I know that little a, because it's the 12.8 meters away from this one building, is 12.8 meters away from the other one. This would be little a, right? So again, this is 12.8. Let's just make this. Again, I could keep the distances if I really want to. It doesn't really matter in our particular case. 12.8. All right, cool. And I know that. And I know this one here, which would be C, right? B over here. Did I make the right thing? A, alpha, beta. Yeah, I was right. This would be little b. Little b is, as an example, 29.5. Okay, I'm trying to keep the same marking scheme or kind of labeling scheme, just so that you guys don't get confused. So this is 29.5. I've got 12.8, and I got this. All right. I want to find this. So Elsa, what do I do next? You're the boss. You tell me what to do. And after this, guys, we can go. Okay? Well, a few more thoughts, and then I'll let you go. Okay? Tangent of what? How do I figure this out? I don't have any information. I don't know anything. I mean, I have a triangle, and beta is outside the triangle. So is that right? Trick, actually. Don't be tricked by this, right? It's a trick, truly, right? Remember we talked about right at the beginning. You missed the beginning, right? Well, we have complementary angles. Remember complementary angles? Well, actually, if you think about this, and I'm sorry to put you on the spot like this, but if I take this, okay, this is actually this. These two angles are the same, yeah? So now that angle is inside of the triangle because there's a relationship. Notice there's a box, there's a square, right? And there's two right angles. There's one right angle over here, right? I didn't draw that right. Not even a square box. Damn it. There we go. And I'll make this no fill, and I'll make a solid line that's red. And I'll make it like 2.5. There we go. So just a little bit. Nudge. Okay. And then there's the right angle, right? But there's also a right angle over here, right? And the thing is, we know that these three angles add up to, these triangles here add up to 180 degrees, but so do these ones. And we know that there's a relationship between these complementary angles, right? That this angle here is equal to this angle here. This angle here is equal to this angle here, right? This angle here is equal to this angle over here. We know that relationship. That's part of trigonometry. So then we don't worry about this one, even though this is the angle of depression that we're really looking for. We can actually put, this is the angle that we're looking for down here. And so that's part of the, when you get a question like this is maybe one of the tricky parts. If you ever got a question like this, you know, that might mess you up. Guys and girls, the test that you're going to get is going to be eerily similar to this. The stuff I'm giving you here is going to be very close. You might get something like angle of depression, angle of inclination, or one of those kind of things, right? So again, now once we've done this, this is the thing. The first thing is getting the picture right. Once we've got the diagram correct, now it's just using what we know. We can use Sohcahtoa, we can use Sine Rule, we can use to solve the triangle or whatever. We're really looking for the angle of depression though, and I do have a relationship that I can use, right? I could use tangent, like you said. The tangent of the ratio of you know, sine over cosine, right? I could do that, right? A or B over A as an example. Rise over run, I could do that. I could also solve the side. Like, there's many ways to do this, okay? I'm just putting it out there to you guys to see which one you could do. You can do Pythagorean theorem to figure out what the length of the side is, and then from there you can use sine law, right, as an example. You can do a lot of things, and we've talked about all these things already. Any questions around basic trigonometry that we've talked about, triangles and angles? That's all I'm covering this session, okay? This should remind you of stuff that we've learned in grade 4 and into high school, okay? It's stuff we've learned. For in terms of mapping stuff, your first assignment will include some of this stuff as well as some other things from calculus, okay? Calculus is going to be part of the next session that we're talking about. Okay, on to calculus. I'm done with this now. On to calculus. One thing I want to remind you of is that next week we start calculus, the first part of calculus, which is limits and derivatives. I've put up, I think, 4 or 5 of my PowerPoint slides up on Blackboard already. And I also have the videos from last semester, the last time I did this. Now, they're mostly correct, I'll tell you this, but we also had a bit of a strike situation about a year ago. So when it comes to the later videos, I may have to remodify those. I'm also re-recording this stuff anyway, right? But you might see a slight difference. Now, however, most of the information that you're going to get in the videos are going to be fairly accurate. So if you read ahead or watch ahead, whatever you want, because there is no textbook required for this course. I'm giving you the materials that you need for the course. It's a good thing. So when you come in on Tuesday, when I see you on Tuesday, if you've watched a bit of the video or at least read through the PowerPoints, you'll be a little prepared for what I'm going to be talking about. Okay, recap. We talked about, you know, these trig and triangles and all that stuff. I also talked about how you're going to get a bonus if you attend class, both lecture and lab, okay? I'm also going to be tracking you with, excuse me, AdClass, and I give you guys an announcement of downloading AdClass, the AdClass app, or, you know, using the web application or whatever, so I can track your attendance and give you the bonus. That's coming up next week. You're going to have calculus. I'm also going to give you assignment number 1 next week. Again, you can do it in pairs. I recommend doing it in pairs, maybe up to 3 people I will allow. And people will say, well, if I do it with 3 people, I'm not going to learn what I need to know for the test. Yes, maybe if you did it that way. For example, if me and Elsa work together, Elsa is my partner, right? What I would probably do with Elsa is say, okay, Elsa, you do your assignment, I'll do the assignment, and then we'll come together and compare. Which one is it? And we'll take the best answers. Some of you may also compare with all of the students in the class. Okay. And you might say, well, I can get perfect this way, right? Okay. You could do perfect on your assignment. But the idea is the test is going to be way harder, right, if you do that. So you need to do some of the work yourself because your test is individual. You need to know how to do the test. And the test is a 2-hour test that's multiple choice, you know, true, false, right? Where you have a scratch pad of paper, that's what you're going to get, and a calculator. So please buy, if you don't already have, a scientific calculator. I'm not going to allow you to use the calculator on your computer, all right? And you can't use the calculator on your phone. You need to buy a scientific calculator for like 20 bucks. You can get it through Amazon. or you can get it through Walmart or one of the stores, okay? Scientific calculator, non-graphing, please. Okay, I need that for your test, which is going to happen on week 5. I'm giving you 4 weeks notice. I am not going to provide extra calculators on site on the day of. The test is going to happen in this room. It's your responsibility to have a calculator, a pencil, an eraser. I'm going to provide paper for you for scratch paper, and you're going to provide a cheat sheet that you print out. You're allowed one cheat sheet that I'm going to give you part of, and you can add to it, okay? There's not going to be any communication. You won't have access to the internet. You're just going to be able to do your test, okay? Questions around anything I've covered so far today or this week? Okay, guys, thank you so much. That ends this session, this tutorial. We're going to meet again on Tuesday, and we're going to start off with calculus, derivatives, and limits.